Okay, so next part of our job is to do something called motion analysis. In order to do this, you guys have to go to this one, SolidWorks add-ins. If you go here, you can check and you're going to see something called SolidWorks Motion. So make sure you turn this on. If you don't turn this on, you can only see, you are not going to be able to see motion analysis here. If you turn this off, you're going to see two things only, animation and basic motion. So make sure turn this on. So we're going to put some motors on our crankshafts. This is our crankshaft. There are a few questions we need to answer. We need to plot. Uh, First thing is graph of displacement of piston versus time. So we got the standard one now, SVA, displacement, velocity, acceleration. And then we can also plot motor torque and definitely motor power. So in order to do this, just go to motion analysis. On our motion analysis, we can see a few things. You can see this one, playback speed. This is animation wizard. This one is auto key. This one is moto. So this one is important. If you need to, this is moto. Next one is a spring. Click on moto. What do we have here? Moto, you've got rotary moto, you've got linear moto. You can set the speeds. Next, let's take a look at spring. You've got linear spring and you've got torsional spring. Anybody know what is a torsional spring? Anybody know what is a linear spring? Let me put a white screen. So linear spring is this one. This is a linear spring. So when you apply force, this one will contract. So this one is a linear spring. So the other one is, I think it's rotary spring. Rotary spring is like this. Rotary or torsional. When you give a torsion, and you give a moment, and then this one is governed by this one, right? F is equal to kx. K is in Newton per meter. Rotary is torque lah. It's already torque. How much torque per angle? What is the spring's stiffness? Most likely Newton meter lah. Newton meter per degrees. Or Newton meter per radian. Newton meter per radian also not so easily imagined. Probably not Newton meter per degrees is better. So yeah, this is torque or rotary. This is linear. Okay. Torsional spring. Okay, next. X. And then you've got damper. You can also put linear damper and torsional damper. What else? You've got force. You can put force torque. Action only. Constant force. Or you can do step force, harmonic force. There are many options you can do here. Other than force, you've got contact, solid body curves. You can set what kind of material, and you can also decide friction coefficient between materials. And then you've got gravity. Gravity is in which direction lah? X, Y, Z. So for starter, we're going to choose moto. Where should we apply the moto? It should be at the axis one. I turn on this one. I can see my axis. This is my axis of rotation, right? So I can choose circle object, or I can choose axis. Also can. And then this is object. If I don't want to do this, also can. I can just choose this one. I don't need the component direction. 100 RPM change to 10 RPM, and then click accept. Motor location. Okay, so that is done. I can change my time. Right click here, edit key point time to 10 seconds. Other than that, I can click on settings here, motion property study. This is where you adjust the accuracy. If your motion is rotating faster, maybe 10,000 RPM, you might need to change the settings for calculation accuracy. Otherwise, you can just stick to default. Other than that, you can click. Yeah, I think pretty much we're done. You can click motion analysis. Is it rotating or is it not rotating? If it's not rotating, there is something wrong with how you set it. Apparently this is being set wrong, but that's fine. Let's delete this and do it again. Delete the motor. Yes. Click on rotate. Click on this circular object, and then again change to the RPM. 10 RPM. Click on accept, and then calculate. Now it is being rotating properly. So motion analysis is done. You can play it back at a faster speed if you want. 2x, 5x, rotate faster. Or just make it like to scale lah, 1x. So one thing for sure, if you start your assembly in this condition, motion analysis will take a snapshot. Take a snapshot at your current assembly position. For example, this is motion analysis kan. Let's say I do another one. This is your model. It's like this. I can rotate it like this. Let's say it's like that. Okay. The motion study is under this condition. If you go to motion study, you can duplicate, create a new motion study. It will take a snapshot of the current state. Motion study 1, the snapshot is like this. Motion studies 2, the snapshot is like this. So it will start according to the final condition of your motion. Put a motor here, 10 RPM, and then calculate. So it will rotate like that. So next thing we should do is we should results and plots. Select a category, probably displacement, linear displacement. Select a component. If your motion is on y-axis only, you might want to change to y component only lah. If you are confident lah. Otherwise, you can choose magnitude. I think everything's in y direction, so y. So we can choose whatever we want to study lah. This one, can I choose more? This one, cannot. Can I choose a lot? Let's say I want to do this one, 2, 3. Cannot cannot be more than 2. Let's say I want to study this one. And then plot versus time. Okay. Accept. Oh, okay. This one is only 5 seconds. I gotta add this key Edit key point time to 10 seconds. I need to recalculate. Then I'll get the whole thing. So I will get a position of highest point to the lowest point, 178 to 102. This is in y-axis lah. This is with respect to the axis itself. Where is our axis? This is our axis. Control 8. This one. Let's say if you were to play again, it will go back to its original. So something like this you can export to Excel. How do you export to Excel? I think this is the results. This one, right click. Export to spreadsheet. Click export to spreadsheet. So you've got this one. This is the plot to Excel. Excel, you can change a few things. On the next sheet, there will be the data. This one is linear displacement in millimeter. 178 is the highest point. The lowest point would be 102. But this one is y-axis. If you were to do more results, you can even plot. Let's plot more results. You can even plot displacement, change to velocity component, y-axis juga. Maybe this one also. So you're gonna get something like this lah. So this is velocity, this is displacement. So you have to study lah. Add more things, probably more analysis. Acceleration, linear acceleration, component Y. Again, choose the same location. This is the acceleration. So if you were to play right now, it will track lah. It will track SVA. So this is easily how you can study motion lah. Other than that, there are more things you can calculate. There is something called forces or moment energy power. Forces, I think you can choose this one. Motor force, no, motor torque. Motor torque magnitude probably. So if you choose motor torque, you need to choose motor lah. Where is the motor? Rotary motor 3. This is the motor torque. This is magnitude. It looks weird. I think I have to change this one. Motor torque, edit feature. Rather than magnitude, you choose X, I think. It's X. This one is okay. X will give you the proper so that's the difference between magnitude and directional. This motor torque, if I change to magnitude, everything will be positive. So the graph looks weird. Never mind. Change back. Change. If you choose the wrong axis of rotation, maybe Y is gonna show 0. Okay. How do you calculate this? Let me put on a white screen. So let's look at your axis. Let's say if your axis is like this. Y. This one. X. This one. let's say, just let's say this is Z. So if you have a shaft like this, if it's rotating like that, so this one is actually rotating in the axis, which is the axis of rotation. Or if this is 10 Newton meter, you can also call it 10I. If it's put in vector format. So if it rotates like this, this one would be Z. Okay, this axis is Z. So remember, it is following the right hand rule, which is if it rotates like that, it's positive. If it rotates like this, it's positive. If it rotates like this, it's positive. If it's the other way around, it's negative. Okay, so this one, all the basics lah. So can you answer all these things? You should be able to do it. Is it jive with your models? For example, if it's like this, bottom and top. What is this distance? Distance measure this point to this point. This point to this point is actually 76.2 mm distance. Is it jive with our results in motion analysis? Where did we see 76.2, was it? Distance 76.2 from the top to the bottom, right? This would be the displacement. Remember, your engine has displacement 76.2 mm. Now look at this one. 178 minus 102. Berapa? Yeah, it's around 76 lah. So how people measure engine size or engine displacement? That would be widescreen. Engine displacement lah. It is the volume inside the cylinder, right? Your piston might be here. Let's say this is your piston. You've got this piston ring, so it travels back and forth, right? It travels up and down. So this is the displacement lah. This is the volume. This height is actually 76.2 mm. So kan kamu punya kereta kan, your car engine is what 1.3 liter. Lagi apa? 1.5 liter. 2.0 liter. So this is the volume of this one lah. The volume of your piston. So the height is 76.2. What is the diameter? Diameter of the piston berapa? That's okay. Diameter of the piston. Let's go to model. Again, evaluate measure. Just click on this one. Area 4560. So 4560 mm square times height lah. right? So you've got 1389888 millimeter cube. This is the engine displacement. So you times 4 because you have 4 cylinder. So now let's convert. Alright, so there you go. It is 1.389. So this engine is actually 1.4 liter lah. 1.4 liter engine.